Now I'd like to go over an overview of our presentation. We will begin with an introduction and motivation, move into theory and project background, discuss Proelia's project, which was comprised of water tunnel testing and afterburner testing, move into safety, budget and team hours, and finish with conclusions and recommendations. I'd like to go over an introduction and motivation. In the fall semester, our preliminary design course, our team designed an air-breathing engine with an afterburner. As seen in the picture, the afterburner is highlighted in red. After researching a lot of different engines in the industry, we quickly learned that afterburner information is considered classified and highly proprietary. And so this led us to, this sparked our curiosity into wanting to learn more about afterburner components, particularly flame holders within the afterburner. So moving into our detail course, we learned that there was a previous detail team on campus called Apex Propulsion, and they had fabricated and manufactured an afterburner. So we inherited this piece of hardware to learn more about flame holder arrangements. In doing so, we decided to move forward and conduct two types of tests: water tunnel testing, in which we were going to study recirculation zone size, and afterburner testing to measure thrust emissions and temperature. And now I'd like to pass it off to Lane Henry.
All right, thank you, Katie. I'm Lane Henry, and today I'll be going over theory and project background. So in theory, afterburners are used to augment thrust that is produced by the jet engine. Typically, they have a 50% increase in thrust from the jet engine, and then they also have a 300% increase in the fuel flow rate. What we're planning to do is take a real afterburner and implement a test section as shown here in the figure by our square afterburner produced from Apex Propulsion. Some of the components of the afterburner that we inherited are the fuel spray bars, which inject and atomize the fuel into the flow. Next, we have the igniter, which is a basic grill igniter, which is used to spark the flow for combustion. And then we have the flame holders, which we will be investigating. They are used to promote and propagate the combustion down the afterburner. And then we have the screech liner, which is used to dampen high frequency acoustic instabilities, and is also used to cool the metal of the afterburner. So for our project, inheriting this afterburner from Apex Propulsion, their goals of their project was to investigate the combustion efficiency of afterburner due to the flame holders. And however, limited data was obtained due to time constraints and material limits reached in measuring the exhaust temperature coming out of the afterburner. However, they were able to conduct water tunnel testing, and they were able to find out that a 60-degree flame holder angle, shown here in this figure, was the optimum angle for creating the best recirculation zone in the afterburner to create the best combustion. So using this information, Proelia Engineering decided to continue on their project, however adding a few components. We wanted to test different flame holder configurations to see what would give us the optimum thrust. And we also wanted to investigate the recirculation zone more in order to allow for that complete combustion. And how we wanted to do that was through water tunnel testing. And we would analyze the flow characteristics coming over the flame holder and analyze the recirculation zone. And how we would do that is by the larger recirculation zone produced by the flame holder configuration, the larger the recirculation zone would result in a higher efficiency of that flame holder configuration. We also plan to manufacture a nozzle, which would augment the thrust produced by the current test rig, and we would attribute the thrust produced to another component of the efficiency of that flame holder configuration. So our flame holder configurations we wanted to test were based on the afterburner's possibilities. Shown here in the bottom figure is a side view of the afterburner where the middle flame holder is in a fixed position and cannot move, and that's where the igniter is placed. The top and bottom flame holders are able to translate 5.5 inches from the front of the middle flame holder. Shown here on the right is the reference condition of our flame holders, where the 3 flame holders are in a vertical in-plane configuration. We plan to test 2 additional configurations, the first of which the top and bottom flame holders are 2 inches from the front of the middle flame holder, and then the second where the top and bottom flame holders are 4 inches from the middle flame holder. Now I'd like to pass it off to Joanne and Marty.
Thanks, Lynn. Again, my name is Joan San Martin, and I'm going to introduce you to one of the 2 tests that we conducted, the water tunnel test. Our main goal with the water tunnel test was to study how the flow behaves around the flame holders. It's quite complex to visualize what's really happening inside the afterburner test section, and the water tunnel, using a hydrogen bubble visualization method, would give us that type of information, that flow visualization of how the flow is behaving around these flame holders and how the recirculation areas are generated. When doing a test like this one, we have to analyze a lot of things, and flow characteristics are very important. We analyzed and we took into account the density, the velocity, and the dynamic viscosity of both the afterburner test and secondly the water tunnel test. Analyzing those parameters, we moved on into modeling the flame holders in order to match Reynolds number. We ended up with a 0.033 feet in height for the flame holder models, and those models allowed us to pretty much match Reynolds number and therefore get actual data out of this test. As I told you in the introduction of this test, we decided to move into a hydrogen bubble flow visualization method. Currently, we did not have a system that would generate these bubbles, so we manufactured one using electrolysis effect. What we did is basically put a positive lead and a negative lead into the water with a power supply of 30 volts. Then we would get hydrogen bubbles out of the negative lead, which is connected to a steel wire, and then placed in front of the flame holder models. From the negative lead, we would get oxygen bubbles, which are placed around a steel stand that will keep the oxygen bubbles to move forward and therefore not get in the way of our flow visualization. We also chose this method of hydrogen bubbles because it's very clean. Usually this type of test use ink, but it requires to clean the water after every test, and that's something that we didn't want to do, so we came up with this idea. Once this analysis was done and this manufacturing was done, we moved into the actual test, and this test required a setup. Obviously, filling up the water tunnel was followed by adjusting the flame holders in the configuration that we wanted to be tested. Then we placed a camera perpendicularly to the flow that would record all the images and all the videos of the flow around the flame holders and the recirculation areas. And then finally connect the hydrogen bubble generator and the power supply. Finally, with the water tunnel test, there is some safety concerns that we have to take care of. Again, we're putting some voltage into the water, and we don't want anyone to get electrocuted. Therefore, we placed a caution tape around the water tunnel so the operators are not near the water while we're testing, because again, there is the possibility of electrocution. Secondly, not for the individuals, but for the hardware, it's very important that we have a correct start and stop procedure for the motor of the water tunnel. And finally, we want to take out the flame holders models after each test, because if we leave them in the water, they can get corroded pretty easily. Now, I would like to pass it to Karen Murphy.
Thank you, John. My name is Karen Murphy, and I'll be going over the results we obtained in the water tunnel test. So, through the water tunnel test, we were primarily just looking at the size of the recirculation zones. We did this through slowing down the videos we obtained during testing and editing the pictures, making it a little bit lighter in order to visualize the flow. The picture you're looking at right now is of our reference configuration, and in this figure, you can see this stand, which we use to hold the flame holders tightly against the sides of the water tunnel. You can also see the top, middle, and lower flame holders, and the recirculation zones, which are indicated by the red ellipses. The white you see in the figure is the hydrogen bubbles generated. We use the grid in the background of the figure to provide us with a reference frame in order to measure each individual recirculation zone. We then added up those areas to come up with a total recirculation zone area. For the reference condition, that recirculation zone was 26.7 square inches. In this configuration, the top and bottom recirculation zones were equivalent, and this is due to the symmetry of the configuration. In this figure, you're looking at configuration 1, where the top and bottom flame holders were moved back the distance of 2 inches. In this figure, when adding up the individual recirculation zones, we were unable to view the bottom recirculation zone, and this was due to the buoyancy of the hydrogen bubbles. However, we were able to assume that the top and bottom recirculation zones were equivalent, and this was due to the symmetry of this configuration, as well as the fact that in the reference configuration, we did measure the top and bottom configurations to be equivalent. Going into configuration 2, which is where we moved the top and bottom flame holders back a distance of 4 inches. Once again, we added up the individual recirculation zones to come up with their total recirculation zone of 44.1 square inches. We had the same problem with the buoyancy effect of the hydrogen bubbles in this configuration, so once again we assumed that the top and bottom recirculation zones were equivalent. In this graph you can see a comparison of the recirculation zones for each configuration. We noticed that consistently across each configuration, the middle flame holder provided us with the largest recirculation zone compared to the top and bottom. However, as far as total area went, configuration 2 produced the largest total area. We believe this is due to the fact that when we moved the top and bottom flame holders back a distance of 4 inches, it allowed the recirculation zones to grow without having any interference on the other recirculation zones. And now I'd like to pass it off to Andrew.
Thank you, Karen. I'm Andrew Bogle. I'll be going over the fabrication for the afterburner test. First, we had to fabricate a nozzle to augment the thrust of the afterburner. We had an estimation of 2100 degrees Fahrenheit of exhaust coming out of the afterburner. So this led us to use A304 steel because it has a maximum limit of 2650 degrees Fahrenheit. The gear train, as you can see on the left-hand side, was used to synchronize the flaps because it is a fully variable nozzle from fully open to fully closed that we would adjust in between testing. And the braking system right here, these bars going across top and bottom, had to be utilized because the gears themselves are not strong enough to hold the weight of the flaps. We fabricated 2 aluminum carts in order to hold the weight of the afterburner and allow them to translate in the track of our test stand, so that when thrust is produced, it would pull on the weight scale, which I'll talk about later. The base had 1/2 inch thickness of 6061 aluminum, which we used because it was easily available in AXFAB of Amarillo. And the wheels had 3/8 of an inch thickness, which allows it to translate in the track of our test stand. The air sleeve that we had to produce was in order to allow the afterburner to translate again. If we were to directly attach it to the blower, it would not be able to move and we wouldn't be able to get a thrust reading. So we attached the aluminum sleeve to the blower itself, and the inlet duct would be able to translate in and out of it. The aluminum allows structural rigidity and a tighter tolerance to prevent airflow from escaping. I'll now go over the actual testing of our afterburner. The afterburner layout, as you can see, incorporates all of our components that we needed for testing. The major components included the propane stand, the air blower and the sleeve, the afterburner itself, of course, and the stovepipe, which allows the exhaust to leave the propulsion lab and exit the building. The sensors that we used to collect our data were the portable scale, which is, you can't see it right now, but it's underneath the afterburner so that when it translates, it will pull on the portable scale and allow us to get a reading in pounds force. The pyrometer was placed on the stovepipe about 34 inches away from the end of the nozzle to prevent the probe of the pyrometer from melting. And the emission sensor was placed outside at a distance of 77 inches away from the nozzle in order for us to allow complete combustion before complete combustion before we get a reading so that the emissions data was more accurate. The actual process of our testing first included starting the igniter on the ignition switch. We would then listen for a spark in the afterburner. As soon as we heard a spark, we would turn off the blower so that when we turn on the 3 propane valves at the bottom, we would be able to ventilate the room before we achieve combustion. And then we would activate the fuel solenoid, which will allow the fuel to flow through the pipes and exit our fuel spray bars inside the afterburner. And as soon as we achieve ignition, we would run each test for approximately 30 seconds at a time. Now I'd like to introduce Siobhan Dressing.
Thank you, Bo. In order to highlight, safety was one of the key aspects of Proelia, and in order to protect the hardware and the personnel, we created a video that highlights some of our key safety features. And after having the safety for the test, we moved on to the risk assessment, where this was an idea from NASA, where we categorized the probability of each event, each hazard occurring, and the level of severity of each hazard. This brought us to 4 classifications: the emergency stop, an undesirable test condition, an advancement with team review, and an advancement without team review. For example, a catastrophic and an occasional occurrence will be classified as 1C. This table above me highlights some of the safety issues into all 4 categories. The highest risk would be a possibility of having a fire, and at this point we would stop the test, use a fire extinguisher, call the fire department and campus safety. Secondly would be a propane leak. This would usually happen before we start our complete test. So we would stop the test and check for the propane leak, shut off the propane, and air out the room. The third classification was electrocution in the water tunnel, and to mitigate this, we placed caution tape around the water tunnel to ensure personal safety. Finally, the sensor data. In case a sensor fell off, we would stop the test and reattach the sensor. This is considered the lowest risk just because it does not put anyone in immediate danger. However, our data would be invalid, so we would require to stop the test. Moving on from this, we came to our preliminary testing. At this point, we were trying to optimize the nozzle. With optimizing the nozzle, this was done prior to any data recording. We kept the flame holders in their reference condition and lowered the nozzle until we achieved maximum thrust on the portable scale. We determined this height to be 2.75 inches, and we ensured that this is the optimum height for the rest of the test, where we will be recording data. This is a video that highlights one of the preliminary tests. So at this point, we ignite the afterburner, and we are stabilizing the flame with the fuel valve and the blower, at which point we make sure the blower is at the optimum position, and we run the test for approximately 30 seconds. The thrust measurement from the portable weight scale is attached over here. Now I'd like to pass it on to Philip Johnson.
Thank you, Siobhan. My name is Philip Chauncey, and I'll be covering the analysis that we did on the afterburner results. First off, we identified 3 testing parameters that we wanted to analyze with the data that we were recording, being thrust, temperature, and emissions data. With the thrust data, we used the portable weight scale to get our thrust measurements, and this gave us a mechanical representation of the amount of thrust that we were producing in the afterburner in terms of ounces and pounds. And then we also recorded temperature data that we acquired through the pyrometer that was placed in the stovepipe, and this gave us a representation of average kinetic energy with the relation of temperature and kinetic energy. And then our emissions data was recorded with the emission sensor that was placed at the end of the stovepipe to collect the exhaust gases and give us a combustion efficiency by looking at the percentage, the change in the percentage of oxygen that was in the exhaust. So after recording those 3 data parameters, we only had time to do 2 tests for each configuration. So we took the average of the 2 configurations for the 2 tests for each configuration, and we placed them in this table above. After looking at the parameters that we were testing, we attributed a weighting factor to each one of the parameters, with thrust having the highest weighting factor of 60%, and then temperature and emissions data having a weighting factor of 20%, and our representation of how important those parameters were to our testing. So as you can see here, the reference condition recorded the highest thrust value, also the highest temperature and emissions data. So taking the data that we recorded, we normalized the data and put them into this criteria matrix and assigned a figure of merit by multiplying each one of the normalized data and put them and rate them by adding up their figure of merit for each parameter in every configuration. And this again shows that the reference condition, by adding up the figure of merit across each configuration, came out to be the top performer in actual afterburner testing. So after gaining the knowledge that we learned from the results that we recorded, we're trying to figure out why the reference condition seemed to have the highest performance out of all the configurations that we tested. So we're thinking about that. So with the reference condition being in line with 3 flame holders in a 4.5-inch zone, we believe that it created a type of wall that created a pressure zone in the area of combustion, and may have sped up the flow of the combustion and actually produced more thrust, a higher temperature, and more complete combustion as well. And then in this test, we also found that the flame holder configuration 2 was our worst performer, and we believe this is due to a pressure loss with the flame holders being spread out by 4 inches. So now in comparison, what we gained from the results in the afterburner and what we gained from the results in the water tunnel, where the water tunnel we're mainly focused on the recirculation zone areas size, and the afterburner we're actually collecting thrust, temperature, and emissions data. And we found that in the water tunnel, configuration 2 is what we believe would be the top performer out of all of our configurations, when in reality the reference condition gave us the top performance out of any of the other 3 configurations. So this is the reference condition right here, and then again this is configuration 2, where the top and bottom flame holders are spaced out by about 4 inches. Now I'd like to hand it back to Katie Sontag.
Thank you, Phil. Now I'd like to briefly go over the budget and team hours. As you can see in the pie chart, our team was allotted $1,500 for the project, and due to the fact that we had an existing rig, we only spent $440, mainly on the components to build the sleeve and the nozzle, as seen in orange. Those were the materials that we had to purchase, and our remaining funds were about $1,060. Presented on this pie chart is a conclusion of our team hours, which totaled 1,000, and the majority of our time was divided between engineering, administrative tasks, and technical work. Now I'd like to move into conclusions and recommendations. After testing, Proelia Engineering learned that our water tunnel results did not support our afterburner results. We believe this is due to the fact that our afterburner does not represent a true model of an afterburner, and we would recommend remodeling components of the afterburner, such as possibly moving the fuel bars closer to the vertex of each flame holder and moving the igniter inside the configuration of each flame holder to more accurately model a true engine. Our second conclusion was that our afterburner produced small amounts of thrust, and we would recommend creating a pressurized zone before the afterburner. This would model more of a true air-breathing engine and would give us better thrust readings. I'd like to thank the following individuals who have helped and supported us during our presentation. And now I would like to open the floor for questions.
First, I'd like to say is really good job, guys. Very impressed with this presentation and what you've done. I have just a couple of questions. I have more, but you guys answered most of them very successfully. The first one is for the water tunnel tests. You mentioned that there may have been issues with buoyancy going over different flame holders. I noticed in the image that you only showed one hydrogen bubble generator. I was curious if there was any reason why you didn't consider using multiple hydrogen bubble generators at the time.
I think due to the size of the test section, we thought that one would be sufficient. I don't know if you'd like to elaborate on this.
The steel wire, can you put the 15 or 16? Oh, since you can see the steel wire in front, and since we're looking the images from the side perpendicularly, it wouldn't really help us much of having another steel wire to the side, because at the end of the day, we're looking to 1D, 1D data, and it doesn't matter if we have more still value because again we're perpendicular to it, and what we're looking is a two-dimensionally.
Okay, I think, I apologize, I think I may have missed that in the presentation. That makes more sense now. My next question is about the sensors used and the data collection methods. I noticed that you all are using a lot of, let's say, analog systems, just recording manually. I was wondering why you chose this method instead of using digital collection systems such as LabVIEW or things of that nature. Why are you using, say, a weight scale instead of a load cell?
I think we chose the sensors mainly because of our budget and also because they would give immediate results. We would be able to record the largest thrust and the largest temperature and emissions data right after testing for quick analysis. I think Karen can elaborate.
We also, as far as giving an example, as far as our thrust measurements, we had a lot of problems trying to find just a load cell that would give us a precise and accurate enough reading within our budget. So it ended up being more simple to actually just get the portable scale, just because every load cell that we tried ended up not even being able to pick up the measurement that we were looking for.
Okay. Just because you came in well on your budget, so I was just curious. My last question was for the nozzle optimization. You mentioned that you calculated the optimum final nozzle height at 2 3/4 inches. I was just curious how that value was determined.
So we would go back. Touch just so that he can see. It's actually you can see
You guys
it.
have like a slide?
Keep going, you're almost there.
Yeah.
That's fine.
That works.
That works. So it was the height between the top flap and the bottom flap, and we just brought them together as we optimized the business.
So what we did was we had a series of preliminary tests, and we would incrementally close the nozzle about 1/4 inch at a time. So we found like, okay, this configuration gives us the most thrust on the digital scale, or this gives us the most stable flame. And then at that point, we would lock the nozzle there and then test each flame holder configuration from there.
Okay, because I was under the impression that that would determine. I think that was all the questions I had. Again, nice job.
So I repeat his comments. That was good presentation. Appreciate it. I liked your risk assessment, hazards analysis. It was good to see that you had safety in mind right off the start. The other results, perhaps it's my understanding, but could you go back to those results analysis for a minute? What I thought I heard you say was a wall was created, which then helped create a pressure zone. But then that resulted in speeding up the velocity through the nozzle. Can you describe that a little bit better for me? A wall to me seems like it's going to be a strict flow, but I'm trying to figure out what you're saying there.
Go to the very last one.
So this is the reference condition that we're saying that it was creating like a wall. The flame holders are actually only spaced by probably less than about a 1/2 inch. So when they're
There's not a pressure wall there.
but there's creating a pressure zone because there's blockage created by those flame holders, and that's where the combustion is happening. And so it's got that buildup of pressure, and then when it combusts, it releases and gives us a little more thrust than the other configurations.
It's not an interference wall.
It's not an interference wall. It's just kind of it's just giving us sort of a wall.
Sort of a wall.
Yeah.
And on your pressure loss, can you describe a little bit how you're measuring those pressure losses?
We didn't actually measure the pressure loss. This was just kind of like our afterthoughts to the data that we recorded. But we thought since, well, the reference flame holder condition was creating most likely some kind of pressure zone that was giving us more thrust, then we probably had some kind of pressure loss by having those flame holders spaced out. Because even in configuration 1, where they're just a little bit closer, it produced more thrust than the second configuration. So there's also some other reasons that we thought of too, that Katie talked about in the conclusions, with having the fuel bars actually right next to the vertex of the flame holders, so that we didn't lose. Because another possibility was that when the fuel was combusted over the middle flame holder in that configuration 2, that it may have been combusting more fuel and may not have even gotten to the top and bottom flame holder being 4 inches downrange.
Okay, then just some basic question here. You settled on 60 degrees for your flame holder angle. Is there any particular reason for that, or do you consider other angles? Or?
It was just prior research by the other detail team in 2012, Apex Propulsion. They did a lot of water tunnel testing, and they tested 30 degree, 45 degree, and 60 degree.
So in your report you cite that reference?
Yes.
Okay. The last thing here is on cost. So I saw there was quite a bit of saving in the cost, and you said it was because someone else had done it. But if I were to repeat your test and have to build it from scratch, did you get an estimate on what they had put into that piece of equipment first?
I believe they spent about $1,000 in their budget, which was the amount allotted for their team. And so from scratch to fabricate that afterburner cost about $1,000.
Thank you.
Same comments, excellent job. I'm really jealous. I never got to do anything like this being a senior. If I wanted to see flames, I would have had to have done things at home, which I did. But this is really neat to see this kind of work being done. I think most of the good questions are gone already, so I'll just ask, what do you think the extension to an axisymmetric configuration would have meant to the results? Obviously, this was done in 2D. What do you think, or maybe my question is, what would you advise the next team coming through, maybe to carry on with this rig? What would you advise them to look at?
I would highly recommend the next team to model the components of the afterburner as seen in industry. At the pictures that are available online, because it's highly classified, you can see that the fuel bars are right before the flame holders. And so by moving the flame holders, as we move them downrange, if the fuel bars were moved downrange as well, that might give more accurate data. As well as the ignition system sitting on top of the afterburner isn't truly accurate to what you see in industry, but moving the igniter within the flame holder structure would better model a true afterburner. And so I would recommend moving forward with that.
And I think the other thing you mentioned was a pressure source
Right.
Upstream of the entire experiment, basically.
I believe we talked about creating some kind of converging, diverging duct after the blower, which kind of would choke the flow before it got to the afterburner. Or it would pressurize it before it got to the afterburner.
So I had very, very nice job.
Thank you.
Any questions from the crowd?
Yes.
Do you think CFD analysis would give some additional insight into your configurations and how you're establishing the pressure zone?
I believe so. I think we didn't get to the CFD analysis due to the time constraint of only one semester, but the previous detail team did do CFD analysis in the water tunnel. And so we did use that data in a sense to establish that a 60-degree flame holder was good, but I think that would highly be beneficial to the team to look at CFD.
Anything else?
You first. Me? So guys, when we build that airplane, will your engine be ready? Will your airplane be ready? I think
It
it's
should be.
fine, right?
Good job, guys.
No, I
You're
know.
loud enough?
Yeah. So what you mentioned in one of the comments about the flame holder and the proximity of the fuel injector. Now, a real afterburner doesn't use propane. So I guess my question is, using propane versus jet fuel, do you think that moving the fuel source closer to the flame holder, do you think that's going to help things or not?
I hope so. I think there's even options of using kerosene, which is just more difficult to work with, but I guess propane would help. What do you guys think? Go ahead.
Obviously, kerosene would represent way better what we're trying to do here. But again, it will be more tough to get the combustion going with this type of fuel, and the propane help us with the time constraint move forward and get the flame going and get the test going. But again, we have more time and more to do research to try to get that flame stable and that combustion going with the kerosene. That would be amazing.
Okay, but can I rephrase that? Propane's gas, kerosene, jet fuel is liquid.
Right.
Okay, so it's already vapor, it's already ready to burn, which might be the problem that you're getting with that primer, that one zone, just kind of having all the gas ready to combust. With a liquid, it has to become a vapor first, and so that's basically what I was getting at. Usually, when you look at the jet engines, it's using that time between when the fuel's injected to when it's actually in the recirculation zone, and that distance is really important. And the reason they're getting closer together is the temperatures are going up. And so they're vaporizing faster, and they may combust too fast, which is maybe the problem you're having. And so that would dictate, moving them closer. So I would agree, propane is a gas you probably would move closer, but that's getting you further away from perhaps what a jet engine might be doing. Maybe it's the same reason, but it's you have to take that into consideration. So, really good job. I enjoyed the presentation very much.
That it? Thanks. Now we got a break.
Right. Yeah. Yeah.
Because there were a whole bunch of other variables that less. All these scores in front. Nice job. Karen.
If you're using kerosene, years ago they were like this far apart in order to atomize this and fall before it got here. As they lost that, what you're saying is you got little layer cuts. But the beauty is you have also got gas and fuel. So that's a win for you. If you try to do what you guys did with kerosene and feed it cold air, you create a can for whenever it lights off. Because that's cool for all the on lights. And then this light is going to so that's why you need almost need a pre-burn, pre-warmer, which means lower on the thing. But if you try to electrically, you'll pull the lights down to the tap. Okay, so you have to do something beforehand, and then do that.
It's too early in the morning.
But pressure measurements without the flame would have told you configuration pressure losses. With the run, you might be able to interpret well, the pressure losses due to non-run and say this is the test. Pressure losses with running is this. Then you can start to interpret what's driving the behavior. It takes a while to develop these thoughts because you're like, you just got to get it right. You're much smarter having fought through it. We should look at this, we should look at this. That was a great slide. That one was started with something. You're done.
Yeah.
So that was pretty smooth transition.
I was worried that we might crack up, but we can look together. I think it's just because
the match, the light bulb went on. Right, you got you showed up, and that person. He's just Armstrong. We really I think he's a. I want a copy of this. Well, you probably have enough for results. Yes, it would be video would be wasted by
Well, we tried to use all of this so much of this stuff is abstract. We just still would test the, like I said, the procedures.
I don't agree. If there's any ideas, I mean, I would love to. I'm sitting here, my junior year, I'm like, I would do this.
One of my first year students interviewed. You get hired, but you read it. Oh, yeah.
I'll say big this. I was surprised that last time he was here. He had this year created. I think it's the time.
I wish you were here. They were always back up. So I think we should be more precise. I wish I was
But they make
That's all. Yeah, that's what we did. We wanted to be.
Yeah.
I didn't really do that.
This will be centrifugal flow systems briefing. I'm going to let the panel members introduce themselves and we'll get started.
Hi, my name is Ron Flood. I'm a senior consultant engineer for Virginia Public Service for Technology Innovation Group.
I'm Jake Walder. I'm with NAVAIR at the China Lake facility.
I'm Josh Johnston. I'm the avionics test lead on KC-46 for the Air Force.
I'm Gary Costantino. I'm a senior flight operations engineer at the NASA Armstrong Flight Research Center.
Go ahead and see your test.
Good morning. My name is Alexander Grant, and I am today with my team going over our final detailed presentation from our capstone design course. Overview, we'll first talk about the team responsibilities, what roles each member had in the process, the requirements and what we were required to do from the RFP in prelim, and what the final product needed to be, our configuration and how we made everything work together, the systems, how they work together, what we had to do in order to achieve that, and what all is contained in them, fabrication and assembly. what we needed to buy, what we were able to fabricate, and how we were able to assemble them and make everything work together. Then we'll go into the instrumentation, which is a very important part of this in order to fulfill our requirements. Testing and what our results were when we ended up being able to test, run all the systems, and look at the rig performance as a whole. And then conclude it and go over a summary of how it went and what our final product is. As I said, I'm the design team lead. Zach Bissonette is in charge of fabrication. Kalen Bessler did pressure instrumentation. Josh Ice with temperature instrumentation. Jessica Hodge did data interfacing. And Mike Burgess, part engineering and all of our CATIA. Background on this project, we have new mechanical engineering courses coming in the next couple of years, and we needed to add more of a hands-on aspect to the thermodynamics and the fluids aspect of those classes. This class is ME446L, which is a thermal science and energy lab. We need in this lab to be able to take experimental data and apply concepts learned in the classroom in order to produce a compressor map and look at the performance of a compressor, in our case a turbocharger. From the RFP, we need to reach all of the operational points that the turbocharger we select is capable of reaching. This means we need to reach its max pressure ratio, RPM, and mass flow. We need to also be able to collect accurate and reliable data, and then also interface this data so the user can pull it from the acquisition system and the computer and analyze it. From there, the compressor map is produced and the laboratory requirements are met. This also needs to meet College of Engineering standards for quality and reliability. A compressor map is the image you see to the right. It is a two-dimensional plot displaying 4 sets of data. As you can see on the vertical axis, where it has pi c, that is the compressor pressure ratio. The horizontal axis is the corrected mass flow going through the compressor. And then speed lines are represented by the black lines going to the right and downward. And the islands you see, contours, are the islands of efficiency, with the smallest islands being the highest efficiency. Conventionally, a turbocharger is used most of the time for automotive applications. It works by gathering exhaust gas from an engine, using that flow and that pressure drop over the exhaust gas to turn a turbo shaft that then compresses air from an intake and recirculates it back into the system through the intake of the engine for combustion. So this is a good idea how it is applied on a car, a diesel truck, something like that. In our case, we don't have hot gas to do that, so we need to drive this turbine wheel with compressed air. So for our rig, we have ambient air going into the inlet, as you can see on the rig by the black inlet, then being compressed, and temperature and pressure data is taken from there. On the turbine side, we have the compressed air source, which is powering the turbocharger and spinning the turbine. And then that compressed air is exiting to atmospheric pressure. I will now hand it off to Mike to talk about our rig systems.
Thank you, Alex. I'm Mike Burgess, and I'll be talking about our rig systems. So here we have our projected rig that we started off with our conceptual design at the beginning of the semester, and here's what we have today. First and foremost, we have our turbocharger. This is the centrifugal flow device that we'll be taking the pressure and temperature measurements off of. Connected to that will be our airflow system, taking compressed air in from the wind tunnel air compressor, as well as our oil system, which lubricates and keeps the bearings at a constant temperature. Second, we have our tubing. This allows us to create back pressure for the compressor side, as well as house all of our instrumentation. So our pressure transducers, there's 8 of them, our thermocouples, which there's also 8, and finally our speed sensor is on the compressor housing itself. The sensors, and then finally we have the air containment down here. The air containment is an aluminum TIG welded box lined with sound deadening foam. This is basically so that way once all the rushing air is out of our system, we can dump it into there and keep the noise level down. Furthermore, we have our dedicated computer. This will take all of the sensor readings and all the data from the DACs and save them into Excel files. Our microcontroller, that's being used to control our butterfly valve. This is an automotive style throttle body that is basically open and closed to create back pressure for the compressor side. And then our DAC. We are currently using two DACs. They're over here on this side. That takes in all of the data from the 17 sensors and feeds it into our LabVIEW code on the computer. This flow chart demonstrates how, in basic, our rig will work. So we have the compressed air coming into the turbine side, spinning the turbine. Along the turbo shaft, that spins the compressor, which brings in ambient air. We take the sensor readings off of the turbocharger, which is fed into the DAC. The oil system keeps the turbocharger lubricated and cool. And finally, all the air is rushed out into the containment box and back out as ambient air. Now on to Zach for fabrication.
Thanks, Mike. My name is Zach Bissonette, and I'll be going over fabrication and assembly. First off, as Mike mentioned, our oil system, due to the OEM nature of the turbocharger and being an automotive application, we chose to mimic a typical engine oil system, matching pressure and flow capabilities, as well as capacity. These were all chosen to be within operating specifications of the BorgWarner manufacturer data sheet. As you can see here, we have our reservoir, which was fabricated in-house. We have our oil pump, we have our lines, our pressure regulator, and our pressure gauge, so we can make sure that everything is operating as planned. Next is our air source. We are using a large root-style Ingersoll Rand compressor in the corner of the wind tunnel line. This has a 100-gallon tank, and it provides 73.44 pounds per minute at 125 psi, maximum operating points. This then feeds to a dedicated 1-inch pipe through the propulsion lab wall to our turbocharger. We have a flexible hose and a diffuser that feeds into our turbocharger system. Next, for air management, we first off the flow regulator coming off the pipe from the compressor. Then this feeds through a diffuser, as you can see here, into a removable flange that we can disconnect the part from the air source, and then the turbo flange itself. Up top here you can see the turbocharger, the piping and the gasket, as well as other tubing that was needed. As Mike said earlier, this allows us to contain and instrument all of our flow. Next, the turbocharger itself had to be modified. Some turbochargers come with flanges for RPM sensors, however, in our case it did not. So using our Garrett turbo sensor, our turbo speed sensor, we submitted a drawing to our machinist, Patrick David, at AXFAB, who machined the flange and tapped the hole for the sensor. That was then installed. As well as on the compressor housing, due to the cast nature of the aluminum, we had to port match and polish all the inlets and outlets of the compressor itself to minimize flow separation and maximize sensor efficiency. Finally, the turbine of the turbocharger itself had to have an air dam welded in. This was a little bit tricky as it is a cast iron housing. However, this was necessary to segregate the wastegate flow and the turbine flow so we could properly meter both. Next, we had to control the mass flow in some way. This was probably the most crucial aspect of the control systems, as without a back pressure, your turbocharger will not create a compression map at all. We use an electronic style automotive throttle body, as Mike said again earlier. We control this using an Atmega 128 and the UK 1122 microprocessor and half bridge. The reason why we did this is so we could modulate the stepper motor inside the throttle body itself with a pulse width, and as well as incorporate fail-safes and some kind of security measures in case of overspool or unsafe conditions. Next, we have our pressure regulation. We use, again, an automotive style boost controller. This is a manual style needle valve. This manipulates the pressure seen from the compressor to the wastegate actuator. The wastegate actuator is on the other side of the turbine housing itself. As you can see here, it operates a door through the actuator itself. It is a spring and pressure operated diaphragm, which then opens and closes this door depending on the pressure seen in the compressor. This allows work air to bypass the turbine wheel itself, keeping the work input to the compressor wheel at a constant rate, allowing the pressure to be set for gas setting. Next, for rig operation, this is probably the most important user interface of the rig itself. The operating idea is to set a pressure by rotating the spool controller, as you can see here on the corner of the cart. This sets a pressure regulator, sets the pressure ratio, as I said earlier, and then using the potentiometer on the cart, you operate the butterfly valve and operate across the compressor map at different mass flows. And then once you have hit all your operational points at that particular pressure ratio, you change the pressure ratio to the boost controller, and then again travel across the mass flow, collecting points. Finally, for sensor implementation, we had to devise a way to instrument both our pressure transducers as well as our thermocouples. Stainless steel nuts were welded onto the tubes that we were taking temperature data on. Then the thermocouples were then threaded onto the nuts. And the pressure transducers, as Kaylin will talk about later, were mounted on a heterostatic tube, and brackets as well as adapters had to be installed and fabricated to mount these properly. Next, off to Josh and Kaylin for instrumentation.
All right, thanks, Zach. I'm Josh Eisen, and Kaylin and I are going to cover the instrumentation of our rig. Like Alex mentioned before, to create the compressor map, we need 3 different types of data: temperature, pressure, and RPM. So we'll need 3 different types of sensors for temperature, pressure, and RPM. For the sensor location and the number of sensors, we refer to the SAE J1723 as a guideline. This is a document put out by the Society of Automotive Engineering that basically gives an industry standard for how to create a compressor map of an automobile turbocharger. So for temperature sensors, most of the research on temperature sensors was completed during prelim. We looked at several different types of temperature sensors initially and narrowed it down to either using thermocouples or RTDs. And we decided to use thermocouples because they are more robust and inexpensive compared to RTDs. And of all the different types of thermocouples, we determined that J-type thermocouple would be the most applicable for what we're doing with the rig. So we tested a couple of industry thermocouples during prelim using an Arduino microprocessor as a data acquisition unit, and found that the response time of them was unacceptable. The response time was about 30 seconds for the thermocouples that we tested. Response time was one of the most important aspects for the temperature sensors of our rig, because we did not want to have to run the rig for excessive amounts of time just to have the temperature stabilized. So we made the decision to design and build thermocouples that we could tailor to the need of our project. So how we did this, we used 20 gauge J-type thermocouple wire with a TIG welded exposed junction for the thermocouple tip, and a pipe plug configuration using stainless steel bolts that we drilled through. So here's a few images of the process that we followed. The first thing we did is cut the thermocouple wires to length, and then we stripped the wires down, and we had to ensure that we stripped them the right amount so that the epoxy would be able to adhere to both the insulation and the bare wire so that the thermocouple wire didn't slip out of the socket. And then during when we initially tried to weld them, we couldn't get the tips to fuse together. We found that we had to apply tension to the tips during the welding process so that they would fuse together and create the exposed junction tip. Here you can see an image of us welding the thermocouple tips and drilling the holes in the bolts. Here is our finished prototype thermocouple that we did testing on. So here's a graph of the VK-Tech thermocouple response time that we tested versus the one that we built. The VK-Tech is the one in blue. As you can see, it took about 30 seconds for it to respond to a given change in temperature, whereas the thermocouple that we fabricated took less than 1 second. So the thermocouples that we fabricated, the prototype thermocouple, worked great, so we went ahead and made all 8 of them for the rig. Like I mentioned before, for the thermocouple location, we used the SAE J1723 as a guideline. We put 2 at the compressor inlet, 2 at the compressor outlet, 2 at the turbine inlet, and 2 at the turbine outlet. And at each location, the 2 thermocouples were wired together in series to create a single average output, temperature output. Here's some images of the thermocouples installed in the rig itself. And for calibration, all 8 thermocouples were calibrated using boiling and ice water as reference points. And we calibrated the data acquisition unit using the instant cal program that was part of the deck. And here's Kaylin with pressure instrumentation.
Thank you, Josh. So the pressure sensors selected for the rig are the Omega PX309. These are pressure transducers that utilize a strain gauge on a stainless steel diaphragm and a Wheatstone bridge setup. These sensors are measuring absolute pressure, and a total of 8 sensors are used on the rig. This is a table comparing the specifications of the rig to the specifications of the sensors. As you can see on the table, the only specifications not met by the Omega PX309 is the temperature, as our calculations show the rig could reach negative 140 degrees Fahrenheit to 340 degrees Fahrenheit, which exceeds the operating temperature range of the sensor. In order to protect the sensors, we are using pitot-static tubes into the airflow. This way, the pressure transducers can get the pressure information from the pitot-static tubes without being directly exposed to the extreme temperatures in the airflow. As far as the hardware to connect the pitot-static tubes to the pressure transducers, we're using a pipe adapter and a pipe plug. The pipe plug was drilled out and then attached to the pitot-static tube using epoxy to ensure that a seal was formed. And then the pipe adapter, the pressure transducers have a 1/4-inch national pipe thread on the end of them, so we wrapped that in Teflon tape to help with the sealing process and screwed that into the pipe adapter. And in order to ensure that our hardware would not leak, we performed a leak test. This was done using a bike pump and a tube connected to a pitot-static tube. The pressure transducer was then screwed into the end of the pitot-static tube, and an oscilloscope was attached to the outputs of that. Once this was done, a pressure level was set and maintained using the bike pump, and the output of this test will be shown on the next slide. And a total of 3 sensors were tested, a 0 to 50 range, a 0 to 100, and a 0 to 200 PSI sensor. And a total of 3 trials were run for each sensor. The results of this test can be seen on this table. As you can see right here, it appears that there was a lot of noise in the system. However, this was thought to be caused by the power supply to the sensors, and it was using alternating current, whereas the sensors required direct current. So it matches up pretty well for each pitot-static tube test. So this will be taken care of in the lab view code itself. And as you can see right here, the averages in between the peaks appear to be fairly constant, which shows us that there are no leaks within the pressure system. In addition to a leak test, we went ahead and also did a delay test to see if there's any delay caused by the pitot-static tube system in place. This is the same setup as the leak test, except instead of setting the constant pressure and keeping it at that, we used the bike pump to induce the pressure, and then we set a timer and recorded how long it took for the pressure transducers to supply an output which matched what the bike pump pressure was reading. This was done with 3 sensors again, 0 to 50, 0 to 100, and 0 to 200 sensor, and these were taken averages of each of the 3 trials for each sensor. The results of which can be seen on this slide. As you can see, the 0 to 200 range sensor had the longest delay of 1.06 seconds. However, this will not be a problem on our rig, as we're using an averaging factor in our lab view and we're taking a large number of samples, so this will average out the lag in the system. To place the pitot-static tubes within the tubing on the rig itself, we're using the document, as Josh mentioned earlier, the SAJ1723 document, and another document published by United Sensor Corporation. According to these documents, the pitot-static tube will be placed 2 times the diameter of the tubing away from the face of the compressor and the turbine. In addition to that, we are placing the pitot-static tube in the center of the tubing to help avoid any boundary layer effects. In this picture, you can see the pitot-static tube is installed on the turbine outlet side and also on the compressor inlet side. It's also been installed into the compressor outlet and over here on the turbine inlet. At each one of these locations, we are getting a total antistatic pressure measurement. The pitot-static tubes themselves are installed onto the rig using brackets, as Zach mentioned earlier. This is one of the brackets we have right there. It helps to stabilize the pitot-static tube and to support the pressure transducers attached to them. And to attach the pitot-static tube to the bracket, we use JB Weld epoxy. To calibrate the sensors, we completed this semester using values provided by Omega with the purchase of the sensors. This is an example of the data sheet they print out with the calibration test that they do in-house. This was done to create a graph, and we were able to generate constants off of that graph in order to implement it into LabVIEW to give us the correct pressure measurements. Moving on to the RPM sensor. The RPM sensor selected is the Garrett Speed Sensor Pro Kit. We're using this RPM sensor to measure the RPM of the compressor. It does this using the Hall effect, and it provides a frequency of the passing blades, which is what it outputs into the DAC. Using the digital counter inside of the DAC itself, we're able to convert the digital signal from the RPM sensor to the frequency and further manipulate that in order to provide an RPM for the students. This sensor requires 5 volts of direct current, and this is directly supplied by the DAC itself. As you can see, there's the modifications that Zach mentioned earlier, and this is the RPM sensor installed on the compressor housing. Moving on to the power supply. The main requirement for the power supply was that it had to provide excitation voltage to the sensors, namely the pressure transducers. These sensors required 10 volts of direct current, and the other requirements for the power supply is it had to be simple to operate so that students could walk in and easily use it in a lab, and it had to use the power supply unit that was currently on the rig. The requirements were met in the design as it was able to step down the 12 volts provided by the rig power supply unit to the required 10 volts of direct current. In addition to that, it only requires one knob to turn on, one switch to operate. It's the main rig power supply switch, and when that is turned on, it then directly supplies power to the sensors too. This is the circuit set up to do this. We have the 12 volts coming in from the rig power supply unit. We have a fuse to protect the sensors in case of a surge in current. There's our 10 volt regulator over there, and these are our pressure transducer lines getting power from the circuit. In addition to that, we have a heat sink on there so that it dissipates any heat generated by long rig run times. This is the power supply unit on the rig itself, and it supplies the 12 volts of excitation. At the beginning of the semester, we wanted to ensure that using one power supply would not affect the data coming out of all 8 of our pressure transducers, so we did a parallel power supply test. This was done using 2 200 psi sensors and 1 100 psi sensor. To do this, they were each individually given 10 volts of direct current, and then the output was read using the multimeter. The next step of this process was to wire all 3 of them in parallel and then supply them with just a single source of 10 volts of direct current, and then reading the output from a multimeter. As you can see in the table, the percent differences between the parallel power supply test and the individual power supply test are shown. And from this data, we were able to conclude that using one power supply will not affect our data. Moving on to the DAC. Our current DAC setup is we're using 2 DACs on this rig. We are using a National Instruments DAC to measure the data or the output from the pressure transducers and from the RPM sensor. Then we're using the measurement computing DAC to measure the output from the thermocouples. We have to go with the 2 DAC setup as our original DAC had a channel that was not functioning correctly and did not have enough channels for all of our sensors to go on one DAC. The National Instruments DAC we are using is the USB 6210. It has 16 analog inputs as required by our pressure transducers and a total of 4 digital inputs for our RPM sensor. It's USB powered and it has a 14-bit resolution. The sampling frequency we have selected for our DAC is 750 Hz for the analog sampling frequency and 80 Hz for the digital sampling frequency. The measurement computing DAC selected is the USB 2408. It has the required 8 working analog inputs for the thermocouples. It's USB powered, it has 24-bit resolution, and it has a sampling rate of 500 Hz. These sampling rates for the 2 DACs were determined based off experimentation to see which sampling rate would reduce the noise in the system and provide the clearest results for the students. Now on to Jessica for LabVIEW.
Thank you, Caitlin. So as Caitlin mentioned, we're using 2 DACs with 1 interface, and it uses the same virtual interface, VI, that's in LabVIEW, and we're using the measurement computing USB 2408 and the NIDAC 6210, and it reads in 13 different data sets. And so that's our 8 pressure measurements, our 4 temperature measurements, and our speed sensor. All of this saves to one Excel document through LabVIEW. And so this is our real-time data collection. This is the front view panel that the user will see to collect the data. And before we can test, we have to go into safety precautions. And so we have shields and our rig placement. And we have a primary shield that's attached to the cart, which you can see here. And then we have a secondary shield that'll be placed here for any users that want to stand to the side of it. And then this rig goes in the corner of the lab with the bell housing that you see facing toward the garage door. And And so that will diminish the chance of a ricochet into the lab, and it puts the outside the lab, which is where a failure would occur if one were to happen. And so personal protective equipment, or PPE, it's required for all machine labs on campus. We have ear protection because we do have loud, rushing air in turbo school, and it's out of a comfort level for a normal person to listen to. And then we have eye protection for any airborne debris, and standard PPE for all labs is closed-toe shoes, all personnel behind the glass shields, and lab monitor present. And so going into testing, after we've all set this up, you have to warm up the DAC 30 to 45 minutes prior to use, so that way LabVIEW can collect your data. And you have to set up the rig in the corner of the lab with the bone offs facing out the guard door, which you can see in the picture. Second, we attach the air supply, which you can see is on the inlet of the turbocharger on the opposite side of the rig with the diffuser that Zach mentioned that we fabricated. And then you plug in the power cord to the rig and stabilize the oil to 35 psi gauge. And so that's the optimal point for our oil system, so we don't have any oil spraying out into our pitot tubes inside the tubes. After you plug it in, you have to turn on the power supply, and you have to ensure that the red wire that goes to our breadboard is attached to the 12-volt power supply on the power supply, which you can see up there. And then you turn on the knob, and that'll set power to your sensors. And then you click on the Run button in LabVIEW, and that'll start your data collection. And it asks you to click on a file name to save, and that'll save as the next available file name, i.e. test 2, 3, 4. After you turn on the LabVIEW, you want to run the rig, and so you turn on the air supply at the wall, which you can see in this photo as a white knob, and that opens the ball valve that'll put the air from the compressor into the rig. Stand behind the black shield to operate, and that's right here with the computer, and then you can see the user interface, which I just mentioned before. This is just another picture. You want to stabilize the RPM so you can get the data you want at the pressure ratios you want. Next is to set the boost controller to a specified value and change the mass flow. And so you can see there's a red knob and a blue knob. The blue knob, Zach mentioned, moves you up and down the compressor map on the pressure ratio, and the red knob moves you across on the mass flow. And so this will give you your data points. And then you want to slowly reduce the air from the wall, and that'll make sure that you don't stall or overspool. And then you want to click stop for your data collection. And this will stop the test. And so going into results, this is the tests we've already completed. This is our static pressure behavior, and so static should go down because you have air rushing over it and that will pull it. And as you can see in this graph, it does, so they're working properly. This is our total pressure behavior, so that really tall top line, that is our turbine inlet, and that'll see the most pressure, and we have to boost it out of the compressor. And so again, our pressure transducers are operating the way they should be inside the rig. And so this is our pressure versus mass flow, which is similar to a compressor map. And so it's difficult to see, but we only have 4.6 to 4.7 pounds per minute of mass flow. And so our data isn't quite what to expect when you look at a normal compressor map. We don't have the mass flow, but currently our system is choking through our feed line from the compressor. And so if you look at the Borg-Warner S1VG, our data is in that red circle. And so we have the pressure ratio, but again, we can't open the valve enough to get the mass flow to flow because we don't have it in the compressor that's supplying that rig. And here is Alex with the report.
Quick overview of labor accounting. So these are our hours, breakdown of hours as you see on your right. That's the aspect of our work that we pay the most attention to and divide up to see how we're doing as far as how much time we're spending in each of those fields. And then the left one is the total hours by the team as a whole put into the project. It's following a standard capstone project trend, and the flat line there you see around week 10, 11, that was spring break, so that's where it kind of flatlines, and then it goes up from there. So our budget to do this, we were very thankful to have the College of Engineering supply a very large portion of that. And so they gave us an estimate of about $5,000 to use for this project. We were able to fall under that, and part of the reason we were able to do that is because we were also awarded an Ignite grant because of its nature in research and scientific education. So technically remaining, we have about $720 remaining, so we did well on the budget, especially considering we had to acquire a very expensive DAC later on in the semester that we did not expect. So to conclude this, rig performance, as you saw from Jessica's compressor map, we're having low compressor efficiency, and this is because those points were really far away from the islands of efficiency that were towards the middle of the map. That is because of the mass flow that this turbocharger is designed to operate at, and the problem with us getting enough mass flow through the turbine to get the work output of the compressor required. This is a simple fix and can be fixed simply by having larger piping going from the air source into the turbine because of its choking problem through all of the valves and corners that it has to go through before it gets to our rig. As far as the deliverable goes, we have been able to show and deliver a quality product to the College of Engineering. There are a few more things that need to be completed, but we did meet our RFP and we did fulfill our requirements. Also, it is reliable and it is giving us consistent data. So we can run one test in the middle of the day when it's hot, 80, 85 degrees outside, get that data, and we can compare it to the data that we could run maybe at 11 o'clock at night outside where it might be 45, 50 degrees, and the results come out the same and the corrected mass flow is the same. So recommendations, we do need a larger air source, we need larger diameter piping. We need a faster computer. That RPM sensor is extremely fast, saying that this turbocharger is capable of 170,000 RPM. And the RPM sensor in the DAC is able to accommodate that. However, the processing power and the RAM speed of the computer is what suffers the most. And also, having one DAC would have been a little bit better. However, DACs with more than 16 channels go up in price exponentially, and the DAC alone would have broken our budget. But we were still able to figure out how to utilize two DACs in one LabVIEW code and have it work correctly. We would definitely like to thank several people who have helped us along this entire process, and this includes from our preliminary design portion. Dr. Mike Fabian, who is our detailed design professor this semester and also provided lots of input last semester in prelim. Dr. Brenda Haven, who was our prelim design professor and has been a big part of developing the idea and the ways that we were going to be able to do this initially. Dr. Matt Haslam for our technical writing and presenting, critiquing, and input, and helping us improve our quality that we're delivering here today, as you see. Dr. Joel Skipper, he helped Zach with the programming of the Atmel 128 board and figuring out how to get that to properly work with the C codes. Mr. Patrick David, who did the machining on the compressor housing and also offered a lot of input during the fabrication process whenever we had questions about materials or the best way to do something so that it was done well and correctly the first time. Also, Mr. Jim Weber for helping us with electronic stuff towards the beginning of the semester, and of course, Mr. Danny Klauser for helping us set up the facilities and make it possible for us to run air from the wind tunnel lab into the propulsion lab in order to do this. I'll now open the floor to questions.
Okay, good job, guys. It's a really good looking product that you've come up with, and I like the style of your presentation. It's very professional. You guys look professional, obviously. I know you put a lot of work. So I'm a test guy, so you guys did a lot of testing here, which is good, but that's where a lot of my questions are going to be related to. So back in slide like 60, 61 somewhere, you guys are talking about your data acquisition system. And so you ended up going with 2 different DACs, which I understand cost-wise why you did it. You needed more channels than a single one could provide. But I'm curious that between the 2 different DACs, you have 3 different sample rates, right? And your end goal is to produce a chart that shows data across those 3 different sample rates. So what did you guys do as far as merging all your data? So obviously you can't take a 750 hertz with an 80 hertz with a 500 hertz and all call it good. So what did you guys do with that?
So the pressure transducers read at a constant rate and they just go. And that's at 750 hertz, 750 samples per second. And so that reads in at a constant, and then the RPM reads in every 80 milliseconds. And so at that RPM, you get 6 or 7 pressure measurements and temperature measurements, because those 2 have the same sampling frequency. And that through measurement computing, you can set that, and that's the timeout block from what I figured it is. And so they have the same output, and the RPM is the one that reads at a different rate. And so it just gives you 1 every time you get 3 or 4 pressure measurements.
Okay, so if you have 3 or 4 different pressure measurements for every 1 RPM reading, how are you merging that data? Are you just picking the first pressure reading for the single RPM rate? Because obviously it can change over time. And it's just, data is a snapshot at any window of time. And you can't just combine the data and tell me that it's good, because in the time window of your slower data, you can have a trend going on with faster data that you need to be able to account for, or
So when you look at the Excel sheet that it all reads into, if you read 88.4, which is 88,400 RPM, and then you get 5 or 6 pressure, 3 or 4 actually, 3 or 4 pressure measurements, they all are consistent. So it's like 12.11, 12.114. And so there's a good average that you can take from them. Some of them, they do jump around a lot, and that's when you have to omit that data, and take the other test data. And so we went through 17 different tests yesterday to get the data we have that we showed you. And so there's just points.
In the future, there's some really rigorous ways of doing that I would suggest you guys look at, because there's different implications. Throwing out the data that doesn't make sense may or may not be the right way to do it based on what your goal is. So just think about that, because how you acquire your data is everything. So,
can I make one comment on that?
Sure.
So, possibly because of the 2 DAC setup, but maybe not entirely, we had issues with LabVIEW and the sampling rates and frequencies. So on top of what Jessica said, we also had to find a combination of all of those that wouldn't cause the code to crash. We decided that since we had enough samples, like she mentioned, that there were enough at this point to prove what was going on in the turbocharger was correct. So part of it, again, like I said earlier, a DAC with more channels, so we don't have 2, and that's probably part of the reason that the LabVIEW code didn't like it. But with the current frequencies we have set up, they work together. So that's another portion of that.
Okay. So the other thing I just want to touch on real quick. So you guys went over safety for the operation, which I think is great. That's something that we do in testing all the time. You don't want to go out and do something that's going to hurt somebody or something. One thing you didn't touch on though was any special operator training or emergency procedures, essentially. You said all the things that you're going to do to prevent it from going wrong, but what if it's a bad day? What if something does happen? What's your plan? What's your response? Are you going to have someone standing next to something, or
Yeah. So if you looked at the facilities that we had, there's a big shutoff valve. That worst case scenario, if none of the other fail-safe systems operate correctly, you can shut the turbocharger off directly from the air source. However, due to the throttle body system and the nature of the turbocharger itself, we have the ability to code in fail-safes to take in data from the RPM sensors that in the case of an overspool or unsafe condition, then we can put it in a fail-safe mode, automatically and override any input from the user itself. So in that case, it is taken out of the user's hands. There will be a manual included with the rig itself to train the user on emergency procedures. We didn't touch on those as a time concern.
Okay, just realize that automation doesn't always work.
Of course, and we have backup lists for that.
I've seen it not work.
Really nice presentation. Can you give me a little walkthrough of how you start up the rig and where you determined that you had reached a test or a test facility limitation? Maybe go back to your final results slide.
Which number one in particular?
The one that shows just the limited portion of the map that you could achieve. Yeah, that one there. So I guess my question, how did you get this going, and where did you determine that the facility was inadequate to get you where you wanted to be?
So as far as inadequacy of the mass flow into the turbine, we did test runs while looking at the data, but not necessarily collecting it or using it for the analysis that you saw. And we looked at where the turbocharger reached its max pressure, what the temps were, what the flow was, and that type of thing. And we figured out where on this map we could get performance-wise. And we were actually able to get, we got a good pressure ratio, as you can see. And we also were able to get all the way over about this point on the mass flow. However, getting diagonally up the map with a large amount of mass flow and a high pressure ratio obviously requires a lot of work. So we figured out where we could get on the map. Because we needed to get a high pressure ratio for the turbocharger for the RFP, that's why we decided to focus on the pressure ratio side of the map and achieve that one.
And one more thing that we wanted to do is with the throttle body system completely open, so no back pressure being built in a free flowing condition. With the air source fully open, we were only able to max out at 120,000 RPM. And that was due to the restriction in the supply hose, which we measured to be no more than 45 psi at the turbine face. So considering that the source is 125 psi or greater, that's definitely a restriction that we have.
So I understand this to be a legacy apparatus that future teams can work on. Can you give them some advice as to what size tubing or shortening the tubing, valvage, so on, to get them where they want to be?
This actually won't be a legacy project. This rig just has a few more tubes to be connected to it, to the sound box, and then we just need the facilities to have piping installed. So once that's taken care of, it will be ready to be used in a lab, actually.
And you can guide that future team as to what that piping sizing should be?
Yes, actually Zach and I will be here next semester probably for sure to work on the rig and get it to that point. Our concentration this semester, due to the semester time constriction and the quality that we really wanted out of what we did did the requirements and knowing what we're going to do from there. The manual that's going to go with the rig, not the final report, but the actual manual will include everything as far as minimum requirements for pipe diameters, maximum head loss that you can have before it gets to the turbine wheel.